in class today we simply went down the list of triangular, what I call, quote, triangular relationships. We'll see what that means in a minute, and talked about some of them to some extent, and saw, what people recognized, what people didn't recognize. So let's just go into a discussion of that. The very first one, we had the list F, M, and A. Okay, well, people immediately recognized that they were related by Newton's second law. Now, we note that F and A are vector quantities, so we write them as such. And we put them in a triangular relationship here, simply indicating that if I know any two of these, I can calculate the third. So if I know these two, I can get this. If I know these two, I can get this, and so forth. Okay, so if we know any two of these, we can get the third. And of course, the relationship is just that F net equals mass times acceleration. Again, vector equation, only mass is a scalar. Now, we didn't, I didn't write down every relationship, just the ones that I thought it appeared that we might want to discuss, or either I had something to say about them, or there was some hesitation on the part of students that made me think, well, we better cover that. So the next one is F, delta S, and delta W. Now, we at first wrote these down without the arrows, and I said, which of these are vector quantities? Okay, and people got it pretty well. The force and displacement are vector quantities. Now, this applies in a limited context, in a context where the force is constant. Okay, and there's some displacement, delta S, and the force acts through that displacement. Delta W is simply, people want to read this as change in work. It's the contribution of work for that interval. So I'm going to write that down. The work contribution corresponding to an interval. If you were doing a Riemann sum, which you would have to do if you had a variable force and were integrating over some path, doing a line integral of force, your Riemann sum would contain work contributions from a number of intervals equal to the number of intervals in your partition. That is, you'd have a work contribution for every interval in your partition of the path, okay, or the variable you're using to parameterize the path. And I'm not going to get into that because we don't really do line integrals in this course, but everybody in the course this semester at least is taking multivariable calculus and know what I'm talking about. When you integrate force, even if it's just an integral of force over a line, okay, a one-dimensional integral, and we have to do that, we partition our interval, and we have a work contribution from every interval of the partition. Okay. In any case, the work contribution due to the force F acting on displacement delta S is what we call delta W, and it's a dot product of F and delta S. And we all know that, and we all should know how this gives us the basis for integrating force over an interval if we do happen to have a variable force that isn't linear. Of course, if the force is linear, we can easily get the average force and multiply it by the displacement. Okay. Okay, now we have F conservative, delta S, and delta PE. Again, F conservative and delta S are vector quantities, and delta PE is change in potential energy. So if we have the conservative force, and this would be the total conservative force, and a displacement, we can get the work done by the conservative force. So I could do this in stages. I could say, okay, well, the work done by the conservative force equals F conservative dotted with delta S. And then knowing that the change in potential energy is equal and opposite to the work done by the conservative force, we see that the potential energy is equal to the negative of the dot product of the conservative force with the displacement. Now, you've got to reconcile this with your intuition. And we've talked a lot about it, and people still aren't there. So be sure you understand the basic definition of change in potential energy as equal and opposite to the work done by conservative force. Okay. Now down here, this might be a little hard to read. This says F net on and delta W net on, and we have delta S. Okay, these three quantities are again in a triangular relationship. If you know any two, you can get the third. Okay, what's the relationship? Simply that the work done by the net force on the system is the dot product of the net force on the system and the displacement delta S. And that delta S, thought I was being careful about labeling vector quantities as vector quantities. That delta S is, of course, a vector, or we wouldn't be able to do a dot product, would we? Okay? Then we have delta W net on and delta KE. And how are they related? Well, this is basic. This is the most basic work energy theorem that we have. It says that the work done by the net force on a system is equal to the change in the kinetic energy of that system. So I have an equal sub D here. Equal sub D means what? Equal, doggone it. Okay? This is fundamental. I find that people have covered this in their dynamics course around the same time we were covering it in physics, 2 chapters on energy conservation. And people still don't seem to understand that the work done by the net force acting on a system is equal to the change in the kinetic energy of that system. Nor do people seem to understand how to derive this, at least in the case of a constant force in one dimension. And we did this, we spent plenty of time doing it in class. You really need to be able to do this. Okay, then we have the fact that the relationship between work done by conservative forces on a system, work done by non-conservative forces on a system on some interval, and the change in kinetic energy on that interval. Now, what's the relationship here? I didn't draw a lot of lines, but of course, this is a triangle. If you know 2 of these, you can find the third. What's the essence of this relationship? Well, somebody did come up with this, said, well, the work done by the net force is equal to the work done by the conservative and plus the work done by the non-conservative, because you break forces, you can classify forces conservative or not conservative. Now, some forces are a little bit of both, but you can still can think of breaking forces into conservative and non-conservative parts. And when you add those 2 up, you get the work done by the net force, because the net force is partially conservative, partially not conservative. And you're back here, and the sum of these is equal to the change in kinetic energy. So in big red letters, we write change in kinetic energy is work done by the conservative force on the system plus the work done by the non-conservative force on the system. And this is a no-brainer if you understand this and understand that the work can be broken into its conservative and non-conservative components, if you wish. Okay? So, these 2 added up are equal to the work done by the net force on. See also what equal sub D means. This is basic, fundamental. This is something that follows immediately from this. And if you understand that, then you understand the structure of the subject much better. You understand what's going on with energy conservation, or at least you have a good context for understanding what's going on with energy conservation.